We want to continue our discussion about identities. We skipped section 5.2, which is proving identities. We're going to do that as we do sections 5.3, 5.4, 5.5. So we don't have to do a separate section for that. We'll do it as we do the other sections. So section 5.3 is called the sum and difference identities for cosine, and I've written these up here. You have them in your notes as always. Notice it says cosine of A minus B. That's the difference formula. It's cosine of A, cosine of B, plus sine A, sine B. So the minus here becomes a plus here, the plus here becomes a minus here. And notice that the pattern's cosine, cosine, sine, sine. Now, be careful. How do you read this expression? It's cosine of A minus B. Students will often see this and interpret this as a product. Because when you see x times y plus z, you say, well, let's distribute. That's xy plus xz. But remember, the distributive property, we say that, but we should be more particular. It's multiplication distributes over addition or subtraction, right? Multiplication distributes over addition or subtraction. There's a multiplication here. This is not cos times A minus B. It's cosine of A minus B. It's not, you can't use distributive law on it. Okay, that doesn't make sense. So my point is, don't do this. Cosine of A minus B is cosine A minus cosine B. That is not true in general. You cannot distribute the cosine. Don't you think if this was the correct formula, we would have used that instead of that mess? That's a lot simpler. We would use that if that were true. Don't do that. Okay. Now, what's the point of these formulas? If you know sine and cosine of A, and you know sine and cosine of B, you can get the cosine of their difference. So there are three angles involved here: A, B, A minus B. Three angles here: A, B, A plus B. So the point of this is if you know things about A and B, you can find out things about the other two angles, A minus B, A plus B. Now, I'm not going to prove the formula to you, but as an example, let's verify that these identities hold for A is 23 degrees and B is 17 degrees. So let me write this one with 23 and 17. I leave a little room on the left. I'm going to work backwards in a minute. So cosine of 23 degrees minus 17 degrees, that's this, is equal to cosine of 23 degrees, cosine 17 degrees, plus sine of 23 degrees, sine of 17 degrees. So everywhere there's an A, I put 23 degrees. Everywhere there's a B, I put 17 degrees. Now, if I typed this whole expression into my calculator just to see what it's approximately equal to, so this whole cosine 23, cosine 17 plus sine 23, sine 17. So cosine 23 times cosine of 17 plus sine of 23 times sine of 17. You should always punch in with me, don't just watch. And I got that that's approximately 0.99452. Now, if you didn't get that same answer, double check and see if you hit a wrong button or what else could be the problem. Did you check your mode? Notice the angles here are in degrees, so your calculator needs to be in degree mode, which mine is. If you're in radian mode, you're going to get a different answer. You're still going to get the two sides to be equal, but you're not going to get the correct answer for what it really is equal to. So 0.99452. Now, if I simplify this side by subtraction, 23 minus 17 is 6 degrees. So this should be the same thing as 6 degrees. So I type that in to get that number. Let me type in cosine of 6 again, make sure you're in degree mode. Cosine of 6 is the same thing. Okay? So the identity, this first identity does work for 23 and 17. Okay, now I'm going to cheat here because I have a whiteboard. I want to do the same thing for the second identity. So the 20, this is going to turn into a plus, and this is going to turn into a minus. So that's not going to be the same answer here, and I'm not going to have the same angle here. What is this angle going to turn out to be this time? 23 degrees and 17 degrees is 40 degrees. So if I take the cosine of 40, I get 0.76604. And that should be the same as if I type this expression in. Cosine 23, cosine 17 minus sine of 23, sine of 17. And I got the same thing, which you should. So this is equal to the same as cosine 40. So again, what's the point of these identities? If I knew the cosine of 23 and the cosine of 17, the sine of 23, sine of 17, I could figure out that that expression is equal to 0.76604. Knowing that, that's the same as cosine 40. So if I knew about 23 and 17 and didn't know about 40, you can use that information to find something out about 40. And you may ask yourself, well, wait a minute, why are we just doing cosine? So the formulas for sine and tangent like these are in the next section. I don't know why they put these in that separate section, but they did. Okay, so let's use this idea to go back to things we were doing without the calculator. The next example says find the exact value of cosine of 15 degrees. Cosine of 15 degrees. Now, if you weren't thinking about what we've already covered up to this point, you might say, oh, well, 15 degrees is in the first quadrant, and so 15 degrees, and label the sides. But what's the problem? We do not have a special triangle with 15 degrees for the reference angle. Okay, so if you thought, oh, maybe we did this back in chapter 2, and you start drawing the picture, realize we do not have a special triangle for 15 degrees. Okay, so 15 is the unknown here, like the 40 and the 6 in my previous example. I'm pretending I didn't know how to find cosine of 40 and cosine of 6 degrees. Right? So I want to find cosine of 15. Well, can I write 15 degrees as a sum or difference of two angles I can do by hand? Remember, the problem said find the exact value, so I can't just punch in the calculator. Can I write 15 degrees as a sum or difference of two angles that we could do by hand? Well, there's probably lots of possibilities here, but one that's popping into my head is 45 degrees minus 30 degrees. 45 degrees minus 30 degrees is 15. Make sure that what you ever put here does add or subtract to 15. 45, I know I can do, because that's a reference angle in our special triangle. It's an angle in our special triangle, as is 30. We have another special triangle for that. So 15 degrees is 45 minus 30 degrees. And now let me apply the top formula here. So this is cosine of 45, cosine of 30 degrees, plus sine of 45 degrees, sine of 30 degrees, right? So this is my A and this is my B. Cosine of A minus B is cosine A, cosine B 30, plus sine A 45 plus sine B 30. Notice I have now, cosine of 15 is now written in terms of four expressions I can figure out. We know how to do those. So there are four things to find here. Well, if you go back to your special triangles, I'll just draw them over here. Right? 45 degrees, that was your 1 square root of 2. And the cosine is 1 over root 2. And the sine is also 1 over root 2. Again, I'm not concerned about rationalization. And now let me draw the other triangle. Again, this is not the scale, but so we're interested in 30 degrees. 30 degrees, your numbers were 1, 2 square root of 3. And remember how you figure out what goes where. The longest side is the hypotenuse. 2 is the largest number, so it must be on the hypotenuse. The smallest side is opposite the smallest angle. That's 60 degrees. And of the remaining two numbers, 1 is the smaller of the two, so that goes here. And the root 2 is here. And now what's the cosine of 30 degrees? It's x over r, or adjacent over hypotenuse, square root of 3 over 2. And sine of 30 is opposite over hypotenuse, y over r, that's 1/2. Again, to multiply fractions, you just multiply numerators and denominators. 1 times root 3 is root 3, and 2 root 2, plus 1 over 2 root 2. Notice I already have the common denominator built in, 2 root 2, so you just add the numerator, square root of 3 plus 1 over 2 root 2. Okay, and there's your answer. Again, I'm not concerned about the rationalization. I'm perfectly fine with that answer. Now, if this is a problem in the book, they're always going to rationalize. If you want to check your answer in the back, you could also check your answer. Type in cosine of 15 degrees in your calculator. Make sure you're in degree mode. Type this expression in. See, you get the same decimal, and you know you got it right. But if you do that, make sure when you type this in, you put the entire numerator in parentheses and entire denominator in parentheses when you type it. So there's the answer. Now, if you want to rationalize, let me come back up here to give myself some room. If you do want to rationalize, just for practice, I have square root of 3 plus 1 over 2 root 2. So to rationalize, I need to get rid of the root 2 in the denominator. If you multiply by root 2 over root 2, that's how you rationalize. So if you distribute here, root 2 times root 3 is root 6. Root 2 times 1 is root 2. And then root 2 times root 2 is 2 times 2 is 4. So this is the answer to this problem they would have in the back of the book. So this is the exact same thing as this, even though they look completely different. Again, you could type that in, type this in, and see you get the same thing in your calculator. So that's how this is the exact value of cosine of 15 degrees. So even though we don't have a special triangle with 15 degrees in it like these, we can figure out the cosine of 15 from two angles we already know. Okay, the next example is similar, but the angle in this one is given in radians. It says cosine, find the cosine of 11 pi over 12. Now, I told you when we first did radians to try to get used to thinking of angles in radians. There's no reason why you can't think in terms of degrees and in radians, just like you think in terms of length and feet and yards and meters and miles. However, on this particular problem, it's not obvious how to rewrite this, break it down. First thing you need to ask yourself, is this an angle that we already can do without doing this stuff? I mean, in other words, can you do this problem from chapter 2 with just using our basic special triangles? Well, one way you can answer that question in terms of if your angle is given in radians, remember our reference angles, 45 degrees is pi over 4, the quadrantals are pi and pi over 2s, 60 degrees is pi over 3, and 30 degrees is pi over 6. So if you have a simplified fraction and your angle's in radians, and you have a pi there, if your denominator is not one of those I just mentioned, 3, 6, 4, 2, or 1, then it's not one you could do from chapter 2. So you have to do it from this section. Now, it's not clear how to do that here, so I know this is not one I could do in chapter 2. I would highly recommend, even though I told you to get used to thinking in radians, converting this to degrees. So remember, this is radians, so I need radians on the bottom, degrees on the top. And then how many degrees is how many radians? 180 degrees is pi radians. And if you do the multiplication here, you get 165 degrees. Okay, so this is the same as cosine of 165 degrees. Okay, now please realize, this is not the end of the problem. I can't tell you how many times students will do the conversion and say, I'm finished. No, the problem wants you to find the cosine of 165 without using the calculator again. It says find the exact value. So this is not the end of the problem, just converting to degrees. Okay, that's just to help us get to the end. Okay, now 165, if you didn't believe me before about we can't do that from chapter 2, right, sketch 165. 165 is in the second quadrant. Now, what's the reference angle of 165? Well, 180 minus 165 is 15 degrees. And again, we don't have a special triangle for 15. The only angles these identities are going to help us find exact values for are angles with a reference angle of 15 or 75. Notice in the previous problem, we did the 15 degrees. So it's not like we're going to get a whole bunch of new ones this way. We're only going to do one with reference angles of 15 and 75. So this clearly is not one with a special triangle. We cannot do this from chapter 2. So we need to rewrite 165 degrees as a sum or difference of two angles you know you can do. Now, there's no way you're going to get 165 out of 30 and a 45 or 60. There's no way. Now, keep in mind, we can find trig values of functions outside the first quadrant. For example, can't we find the cosine of, what do I want to use here? say 330 degrees? Yes, because the reference angle of 330 is 30, right? All the way around is 360, 360 minus 330 is 30. So if I wanted to put 338 degrees here, I could, because remember, the angles A and B you have to be able to do. You find trig function values. We could use 330 if we want to. So any angle that has a reference angle of 30 or 60 or 45, you can use. Now, don't ever put 90 degrees or 180 degrees of quadrantal, because if you can't do this one, if you put a quadrantal here, you're not going to be able to do the other one that you need to make it true, okay? So never choose a quadrantal here. It's not going to help you. What I usually do, pick an angle I know I can do, like 30 or 60 or 45, see what needs to go here and see if I can do that one as well. For example, I'm just going to pick something. Suppose I'll pick 45 degrees here. If I put 45 degrees here, well, what I need here to get the sum to work, I have to use 120 degrees, wouldn't I? 45 and 120 is 165. 45 I know I can do. Can I find cosine and sine of 120? Well, let me draw the picture and see. 120 degrees is in the second quadrant, and the reference angle is 60. So I can do 120. That's the game I do. Pick an angle you know you can do. 30, 60, 45. Find an angle here that either add or subtract that could go with it to make it equal to this. See if you can do that one. Now, is that the only possibility? No. What if instead of 45, I had used 30? Right? If I had used 30 here, I could have used 135 degrees. That would be 165. 30 I know I can do. Could I do 135? Well, there's 135. What's the reference angle? It's 45, yes. So there's more than one way to break these out. Okay, so I'm going to stick with what I chose there. So cosine of 11 pi over 12 is cosine of 165 degrees, which is cosine of 45 degrees plus 120 degrees. Now use the identity. I'm using the second one here. So this is cosine of 45 degrees, cosine of 120 degrees, minus sine of 45 degrees, sine of 120 degrees. So there are four things to find, just like before. Okay, I've already started my picture for 120 degrees here. Again, the numbers are 1, 2, square root of 3. 2 is the largest number, it's on the hypotenuse. 1 is the smaller of the remaining two, it's opposite to 30 degrees. And then root 3 is over here. And don't forget to check for negatives. In the second quadrant, x is negative. Y is positive, R is always positive. So look at my picture. Let's do the cosine of 120 degrees. Cosine is x over r minus 1/2, or adjacent over hypotenuse. Sine is opposite over hypotenuse, or y over r. So there's your 120. And again, the 45 degrees, we just had this as a longer, I think. 1 square root of 2. So the cosine of 45 is 1 over root 2. The sine of 45 is 1 over root 2. So when you multiply across, you get minus 1 over 2 root 2 minus root 3 over 2 root 2. And I have a common denominator. And you subtract minus 1 minus root 3 is minus 1 minus root 3. Again, you don't have to rationalize. If you want to rationalize, multiply by root 2 over root 2. Now let me see if I did that right. Let me type this expression in, the number in, and see what I get. Again, if you want to type this in, put parentheses around the numerator and the denominator. So parentheses minus 1 minus root 3 divided by parentheses 2 root 2. Parentheses. Close it up. It's about minus 0.9659. That should be the same as cosine 11 pi over 12. Now be careful. If you want to type this in, you have to be in radian mode. I just changed mine. So cosine of 11 pi over 12. And I got the same thing, which I should have. Okay, so there's two examples of just computing. So finding exact values of new angles we couldn't do in chapter 2, but we're basing it in terms of angles we could do in chapter 2. Now, the next example is proving an identity, which is really in section 5.2. Like I said, I didn't feel the need to do everything in 5.2 because we can do it in these sections just as individual problems. So it says, prove that cosine of 90 degrees minus theta is equal to sine theta. So so this is an identity. We did this a long time ago. I don't always think of it this way. Remember when we had trig equations and we got down to something like sine of A is cosine of B? And I always said sine of, and we assumed A and B were acute angles. Sine of an angle is cosine of another angle. When could that be true? When the angles are complementary. So we assumed A plus B was 90 at that point, right? So that's what this is saying. Cosine of one angle is sine of another. When can that happen? When the angles add to 90, which they do. 90 minus theta plus theta is 90 degrees. So this is just that same identity we used before. But they want us to prove it. I proved this to you before drawing triangles. I drew some triangles and we convinced ourselves that this would be true. But now they want us to prove it using this. So they're saying show that this is an identity. So the standard procedure for showing something as an identity is you start on one side and work your way to the other using other things. Typically, I start on the more complicated side because it's easier to destruct than it is to construct. If you start with something simple, it's hard to build. You don't know what to do first. But if it's complicated, then you might want to try to simplify. So I'm going to start on the left. Always write down the side you're starting on so I will know. Not everybody's going to start on the same side. So cosine of 90 degrees minus theta. Now notice, think about what you're trying to get to. I'm trying to get to sine theta. So I don't want this angle 90 minus theta, I just want the theta. And plus I don't want a cosine, I want a sine. So what's the clue to use these formulas? I know it's in this section, but what's the obvious reason? This side, the angle's 90 minus theta. This side, the angle's just theta. I need to extract the theta from this subtraction. What do these identities do for you? If you start on this side and go to here, it breaks up your A minus B or A plus B into A's and B's. So I want to just get theta by itself. That's a dead giveaway to use this identity here. Let me rewrite this. So cosine of 90 degrees minus theta. So I'm going to use this difference formula right here. So cosine of 90 minus theta, that's cosine of 90 degrees, cosine theta, plus sine of 90 degrees, sine of theta. So A is 90 degrees, 90 degrees, 90 degrees. B is theta, theta, theta. Now, we're not quite there, are we? We're trying to get, always every once in a while, look and see what you're trying to get to. We're trying to get the sine of theta. Well, I don't know what to do with cosine theta or sine theta, but we can figure out sine and cosine of 90 degrees, can't we? So in the previous examples we did, we weren't proving an identity, but there are 4 things to find, and we could find all 4 of them. Here we can only find 2 of them, the cosine 90 and the sine of 90. Well, that's a quadrantal angle, so I'm using the unit circle here. Pick the point 1 unit away from the origin, that's the point 0, 1, right? 0, 1. Remember, cosine is the first number, so cosine of 90 is 0, sine is the second number, 1. And lo and behold, when you multiply 0 times cosine, 0, that's gone. 1 times sine is sine. And so cosine of 90 degrees minus theta is sine theta, which is what we were trying to get to. So it's not a hard problem, but again, this is easy. That's stuff we've already done, and that's just arithmetic. But the new thing is here is rewriting. We're trying to get to sine theta. I need this angle by itself. I need it separated from the 90. And that's what these identities do for you. It breaks up the angles. Notice if you have something like this and you go this way, you can go this way or this way. If you have something that looks like this, notice it's taking the 2 angles and combining them. But this way, they break them up. So that was a clue to use this and write it this way. Because I had 90 minus theta, and I'm trying to go to theta. If there had just been a 90 over here, I still would have used this because it would have said I need the 90. So you need to break those up. So that's how you do that. Oh, the next question says, what if this problem had been in radians? What would it look like? So the only thing to change the radians here would be the 90 degrees. 90 degrees would be pi over 2. That's how that one would look like. The reason why I mention this is when we learned this identity before, sine of one angle is cosine of another. When could that happen? When the angles are complementary. We did it in degrees, not radians. So be aware that if you were working in radians, this is what it would look like. These 2 identities are true whether you use degrees or radians, right? Just be consistent. If these are in degrees, these are in degrees. Don't put radians here and degrees here, you know. I mean, it would still be true, it just looks messy there. So if your angles are all in radians or all in degrees, they work. Okay. Lastly, this example says, let me write down everything they tell us first. They say sine of angle S is 2/3. Sine of angle T is negative 1/3. Angle S is in the second quadrant. Angle T is in the fourth quadrant. Interesting. So let me pause here. Do you actually know what angle S is? Or do you know what angle T is? No, you don't. But you know a lot about S and T. You know S is in the second quadrant. You know one of the trig function values for S. You know T is in the fourth quadrant. You know one of the trig function values for T. We're going to draw pictures of S and T. We can get a good picture of S and T. Okay? Now the problem says, let me just write the first one. It says find the exact value of cosine of S plus T. And then do it also for S minus T. Cosine of S plus T. Now this is not a trick question. What information in the problem is given to you about the angle S plus T? And the answer is nothing. Oops. This is S. This is information about S. This is information about S. This is information about T. This is information about T. They didn't tell me anything about S plus T. But that's what they want you to find the cosine of. So you don't know anything about S plus T, but you know a lot about S and a lot about T. What is that begging for you to use? It's the same argument I used on the last problem. I don't know anything about S plus T, but I know about S and I know about T. So you want to rewrite this using the sum identity for cosine. Cosine of S plus T is cosine S, cosine T, minus sine S, sine T. So to get the cosine of S plus T, I just need to find these four things, which I can find. Right? So it's just like the problems we did before, except for I don't know S and T. Be careful. S is not 2/3. S is not 2/3. The sine of S. I do not know what S is. My point being, do not put 2/3 for S. There are four things to find here. Sine of S is 2/3. Do not put 2/3 in for S. 2/3 is sine S. The whole thing. I don't know what the angle S is. Okay? Now what else do we know? Sine of T is minus 1/3. T is not negative 1/3. Sine of T is. So instead of sine of T, I have negative 1/3. So just from what was given, I can fill in two of the values. So we have to find these other two. Well, we can do this by drawing some pictures, can't we? Let's draw a picture of S and draw a picture for T. So S is in the second quadrant. Again, I don't know the rotation. I just like putting in something in. So there's possibility for angle S. S is in the second quadrant. Sine of S is 2/3. So sine is y over r, or opposite over hypotenuse. So there's sine. We did these problems like this before, drawing the pictures from this a long time ago in chapters 1 and 2. So how do you figure out the other side? Be careful, this is not a special triangle. It's not 1, 2 square root of 3. This is not a special triangle. Just use Pythagorean theorem. We call this x. X squared plus 2 squared is 3 squared. It looks like x is going to be root 5 if you work it out. Right? Root 5 squared is 5 plus 4 will be 3 squared. Right? So that squared plus that squared. But be careful, in the second quadrant, x is negative. So it's negative root 5. Let me go ahead and fill that in since I have the picture. What's the cosine of S? It's this x over r adjacent over hypotenuse. So it's minus root 5 over 3. So there's cosine S. Do not put root 5 over 3 in for S. It's cosine S. Now we have to do the same thing for T. T is in the fourth quadrant. Again, I don't know the rotation. I'm just going to put something in. So there's T. Please label. There's S and there's T. Don't just draw a picture. Label your angle, please. Sine of T is negative 1/3, so that's opposite. And hypotenuse, clearly the negative is going to go there because r is positive. Okay, so now what's the other side? Again, use Pythagorean theorem. X squared plus y squared is r squared. That's going to be root 8, or if you like, that's simplified to 2 root 2. I'm fine with root 8, right? Root 8 squared is 8, plus 1 squared is 1, gives you 3 squared is 9. So now what's the cosine of t? Cosine's adjacent over hypotenuse, or x over r, that's root 8 over 3. So we have all of our numbers. All we have to do is do the multiplication. So multiply fractions, multiply across. Root 5 times root 8 is root 40 with the minus up front. Over 9. And then minus, that's minus 2 over 9. So this minus is for that one, that is for that one. And now we have a common denominator. We just have to subtract minus root 40 minus minus 2 is minus root 40 plus 2. Again, in the back of the book, if this is probably in the back of the book, they're going to simplify this because I didn't simplify the root 8 to 2 root 2. So they're going to have 2 root 10 instead of root 40. So that's that. And then the second part, which again, I'm going to take license because I'm using a whiteboard here. So the second part says, do the problem again, but find cosine of s minus t. Well, I'm just going to change, again, you need to rewrite this nicely in your notes. But if I change cosine f plus t to s minus t, how's the solution going to change? Well, cosine of s minus t, there's going to be a plus here. So that minus turns into a plus, which means this minus turns into a plus, which means this minus turns into a plus, and then you have minus root 40 plus negative 2, and then that turns into a minus. So that's the only difference. That's the only difference. Now, a common question that they will ask in some of these problems after you're finished is, in which quadrant? Well, I guess we can't do that here. Well, let me just look at the one I have right here. In which quadrant is s minus t in? Could you narrow it down? Okay. So we can't be precise because we only have the cosine. The cosine of s minus t here is negative, right? Negative root 40 minus 2 over 9 is a negative number. And where is cosine negative? Well, cosine's negative in the second or the third. Okay. So s minus t, because the cosine is negative, I know s minus t is in the second and third. I don't know which one. I'd have to know another trig function value to narrow it down even further, and we just know the one. Where was s plus t? S plus t was minus root 40 plus 2, which is still negative. So s plus t is also in the second or the third. I don't know which one, but it's one or the other. Now be careful. You can't play games like this. Oh, where's s minus t? Well, s is in the second, t is in the fourth, so s minus t is in 2 minus 4 is the negative second quadrant. You can't do stuff like that. Or s plus t. Oh, it's second plus the fourth is the sixth quadrant. You can't do stuff like that. Right? You can have 2 angles in the first quadrant whose sum is in the first quadrant. You can have 2 angles in the first quadrant whose sum is in the second quadrant. So you can't play games like that. You have to do what I did here. Once you get a cosine value, is the value positive or negative? That'll tell you what quadrants the angle could be in. So that's the sum and difference formulas for cosine.